Okay, so today we'll look at dynamic models and stationarity. What I would like to start with is, as usual, just looking at what we've done last week. So what we've done last week, we looked at, we discussed autocorrelation, and we explained how the classical linear regression model assumed that the covariance between any two error terms ui uj should be 0, so it's expected to be 0. So the autocorrelation happen when this is not 0, and this is where the problem came from. In the case of autocorrelation, so with the presence of autocorrelation, OLS estimators still unbiased and consistent, but no longer efficient. This is all what we discussed last week. Of course, hypothesis testing procedure becomes suspect because since the estimated standard errors may not be reliable, that means we can't rely on the estimated standard errors, and I show you how to correct for this, but we'll come to this point later. The way to detect for autocorrelation, you could plot the values of the residuals, and then if you see if there is any pattern that you can see, then probably you should suspect the presence of autocorrelation. Or you can do a Durbin-Watson test the same way we explained last week, or Prosh-Godfrey LM test. How to correct for this? There are different ways. You could we discussed how can the first difference correct for autocorrelation, or you can use the heteroscedasticity autocorrelation consistent standard error method, this one. Or today we'll see how, if you introduce some lags, probably it may help to reduce or to eliminate the autocorrelation problem. The other topic we looked at, we discussed also specification errors. We understand that the classical linear regression model assumes that the model is correctly specified, and we explain what we mean by correctly specified. We discussed four different cases where there's problem with specification, so when we have specification errors. So the first one is the underfitted models, where we have some omitted variables. So there are some variables that are important and they should have been in the model, but for some reason they are not there. The effect goes to the error term, and then that causes omitted variable bias, and we explain how to deal with that. The other case where we have overfitted models, when you have irrelevant variables that are not important in explaining the y variable or the dependent variable, and you include these in the model, and we explain how to detect for this. You can use the exclusion restriction if test, the one that we did in the first lecture. The other two cases we looked at is the incorrect functional form and the measurement errors. Today, as I said, these are the two topics I want to discuss with you today: dynamic models, stationary vs non-stationary series. So we'll start with the economic theory. So economic theory is often stated in static or equilibrium form, meaning when we look at the law of demand, when we look at the mechanism by which the price of any commodity is determined, we're looking at that point where quantity supply equal quantity demand, and that's how the price is determined. So we're looking at actually one point, but it doesn't happen that way. It is not static process. There's a process take place until we come to that point. Okay, so that's why we say the theory is usually expressed in a static or equilibrium form, but this is not the case. So there's some kind of process trial and error first, which takes time until we come to this point, the equilibrium. So neglecting the dynamic or the time aspect of any model, that could be another form of a specification error that is related to what we discussed last week. So it's important to think of the time element or the dynamic aspect of any model. So a very popular example of this is the permanent income hypothesis by Milton Friedman. What does this say? It says that current consumption is a function of permanent income. So it's not just a function of the current income xt, is a function of previous income as well, or the weighted average of quarterly income going back 16 quarters. So if you go back to the paper or this this paper, you'll see that the model they estimated went back to 16 lags in time. So that means xt, this is the income in time t, so this is the current income. Yt, this is consumption in time t, and this income in time t is not the only determinant of yt, or the consumption in time t. Also, income in previous time periods also have some impact on consumption in this year. And as I said, in this paper, they went back to 16 lagged quarters. This was like quarterly data. So that's as you can see. So what we looked at so far is this part of the model. So we looked at this. When yt depend on xt, also yt, the dependent variable, depends on the independent variable in time t, so the current value of disposable income. But according to this permanent income hypothesis, this is not the case. It's actually determined by lagged or income lagged in 16 quarter in the past as well. So this will take us to the model that we want to look at today, so which is called the distributed lag model. Current value of y is affected by current and lagged values of x, as you see. So one comment, or we can say about the this equation. So first one is the beta 0, which we call the short-run effect, or this is the immediate impact of any change in the current income, and how this is going to influence or to affect the consumption expenditure. If the change in x is kept at the same level, thereafter, that means beta 0 plus beta 1, this will give us the change in the next period. So if you think of this as, if you think of this part of the equation, that means if you, the impact of these two on x, on yt, will be the sum of beta 0 and beta 1. So if you think of these all as like intermediate impacts between like of income on y, or the consumption expenditure, so then you probably need to sum up beta 1 up to beta 15. So that's what happened in the or what we call the intermediate impact, or intermediate multiplier. Okay, so this is the main idea. So if we have like a more general form of the model, let's say we have k lags. So in the previous model, the one that I showed you in the first slide, in this slide, we go back to 16 lags. You go back in time, 16 lags, or 16 time periods in the past. But if we look at a more generalized form of this distributed lag model, so beta could go back to k lags. So we'll have beta k, and then the sum of all these betas starts from beta 0 in our example, start from beta 0 to beta 16, because we had 16 lags. Yeah? So start from beta 0 to beta 16, or if you want to look at the more generalized form, so start from beta 0 to beta up to beta k. This is called the long run, or the total multiplier, and this gives the ultimate change in mean consumption expenditure, which is yt, following a sustained unit increase in the income. So you see the difference now from this sort of model that is more dynamic, that takes the time element into account, and what we discussed before. What we discussed before, we looked at a model where we have yt on the left-hand side, xt on the right-hand side, but now in this model we have lagged values also of xt. So we see how income in previous time periods, how this would affect consumption expenditure this time period, or in time t. So for example, let's assume now that we have this model where yt depends on xt, xt minus 1, xt minus 2 up to xt minus 3. So let's just think of this as the same way. This is consumption, so we follow the same example. So this is consumption, this is disposable income. So xt here is disposable income in time t minus 1, t minus 2, and t minus 3. And if we assume these are quarterly data, or annually, then that's what t represents here. So the impact multiplier, or the short run effect or impact, will be 0.4. So this is beta node, this is beta 0. Okay, so this is the estimation of beta 0. Okay, so we'll come to the point how we estimate this now. So far, just let's assume that that's what we estimated, that's what we have. These are the coefficients we have. So how we gonna interpret, or how we look at these coefficients? As I said, so the first one, which is the coefficient associated with the income in time t, and the current income, is 0.4, and this is called the impact multiplier. And the interim multiplier, which is intermediate impact, what we explained, so it's actually 0.75. So where this 0.75 come from? It's up to here. Do you remember? So before the last one. So if you add the last one, this gives you the total or long run multiplier. So the final or the ultimate impact of a sustained change in XT, or in disposable income, will have this impact on the current consumption expenditure. So let's put this in an example. So if we say if income increased by $1,000 in year T, or in time T, assuming that this increase is maintained, so that means consumption will increase in the first year by, so 0.4 times 1,000, that give us $400. That's the first year. The second year, it will increase by 200. So it's 0.2 times 1,000. So, and then this, the third year will be 150, and so the total increase will be 850, and that means out of these 1,000 at the end, ultimately, this consumer will be saving 150. So this is not the problem now. This is just a demonstration of what we should understand from these coefficients. So the problem now is how we're going to estimate these coefficients. So how we're going to come up with these numbers that we look at now, these coefficients, 0.4, 0.2, 0.15, 0.1, etc. So if we use OLS, isn't a good idea for many reasons. First of all, how would we decide on the number of lags? So how many time periods in the past we go back to? So this is one thing. So how many lags we would, but also when you add more lags, that means less or fewer degrees of freedom, and this may affect the statistical inference, especially if you have a small sample. And also the more lags you add, the more likely that these will be correlated, and this will cause multicollinearity. And this is the issue we discussed in the week before last week. Okay, so again, so these are like some issues with how would we estimate a model like this, a distributed lag model like this, and if we use OLS estimation. So a correct distributed lag model is just a transformation of this model to a different sort of model that we, some kind of transformation, if we do, we might be able to estimate this model. So first, let's look at the general form. Let's assume that we have infinite distributed lag model. So the difference between this and the one we saw in the previous slides is that the other one had 16 lags, or in the previous slide we had only 3 lags. So this one had 16 lags, the first one, and then this one has 3 lags only. But now let's assume that we have a more general, or this model in a more general form, where we have infinite number of lags. So we didn't define the length of the lag here, so we didn't decide on how far back in time we want to travel, so how many lags in the past to include. And then let's think of this, what correct distributed lag model does. So the idea here is that you can, if you think of the betas, because this is what we want to estimate here, these betas, these parameters, we want to estimate these parameters. But now, if we have infinite number of parameters to estimate, this is something impossible, okay? It doesn't matter how large your sample is, it's something very difficult, and sometimes I don't think it is possible. So what it does, it uses the geometric probability distribution to estimate these parameters. So what it does, it assumes that all beta coefficients in equation 3 have the same sign. So that means, and also to assume that they will decline geometrically following this formula here. So beta k will equal beta 0 times lambda raised to the power of k. So k here is the number of lags you will include. Okay, and lambda here, so k here could be from 0 to infinity, so it goes to infinity. So lambda, the value of lambda will be between 0 and 1, and this is called the rate of decline of decaying. And this 1 minus lambda will determine the speed of adjustment, or how fast consumption expenditures will adjust to the new income level. So how does this work then? So first of all, let's just think for a minute about what this beta k in equation 4. So one, if we look at the lambda, the value of lambda, this one here, so as we said, it's between 0 and 1. So if it is closer to 1, that means that beta k declines slowly, and that means x values in distant past will have some impact on the current value of y. But if we have lambda close to 0, that means the impact of x in distant past will have little impact on current y. So what are we gonna do with this then? So let's go back to, or let's look at the main like the calc transformation. So this is what we did here is just we replaced beta k with its value from here. So if you go back to this slide, so just remember beta k, so beta 1 will be equal to beta 0 times lambda raised to the first power, yeah? Beta 2 equals beta 0 times lambda to the second power squared, okay? And the same thing, so it continues that way. So if we look at this, so we just need to introduce this in this equation. So that's what we have here. So we have beta 0 lambda, so this is beta 1, okay? So this is beta 0 lambda squared, this is beta 2. This is beta 0 lambda to the third power, that means this is beta 3, and so on. So what does this make now? So how does this help us? So in the other one, you see in the original model here, you have infinite number of parameters to estimate. But if we use this formula to do this transformation, so if you have another equation of yt minus 1, you multiply by lambda, you subtract these from each other, then you can come to this form. So transforming this model from this form to this form leave us with 3 parameters to estimate rather than, instead of, infinite number of parameters to estimate. So you see how useful this is. So transforming the model from this form, where we have infinite number of betas to estimate, to another form of the same model that could that we need only to estimate 3 parameters. So these are the parameters we need to estimate. So what happened here again? How we came to this point? So again, from this equation, so if you have another equation of yt minus 1 multiplied by lambda, and then you subtract these from each other, you should come to this form, or this equation. So this is a coic transformation. Coic transformation here leave us with 3 parameters to estimate, and also this is a new form of error term, or composite error term, where this one will equal ut minus lambda ut minus 1. So this is the main advantage of having this. So if you notice now, you should notice this now. Now we have the dependent variable in lagged in the first lag form in the right-hand side. So we didn't have this with the distributed lag model. So if I go back to this equation, so you don't see yt minus 1 on the right-hand side. Okay, so we transform the distributed lag model into another form, which is the autoregressive model, meaning that yt, so the consumption expenditure here, depends on itself, the value of y on its own values in the past, in t minus 1. So this is the first time we see this now. So we see the dependent variable in the lagged values of the dependent variable in the right-hand side. And that's why it's called autoregressive. Autoregressive model means that we have the YT, or the consumption expenditure, depends on its own lagged values in the past. So again, that's why I said, instead of estimating infinite number of parameters, all what we need to estimate here is only 3 parameters. Okay? So now we move from having a distributed lag model to have autoregressive model where YT depends on XT. So this is income in time t, and this is consumption expenditure in time t minus 1. Okay, so this is an autoregressive model, as we say. So the impact of a unit change in x on the mean value of y will have, again, so we'll have the short run impact, which is the coefficient of the income in time t, so beta 0, and the long run impact can be obtained by dividing beta 0, this one, divided by 1 minus lambda. That will give you the long run impact. So we understand that, and this is what we assumed when we did the correct transformation, that the value of lambda will be between 0 and 1. That means the long run impact will be greater than the short run impact. So if you think of this term, so if this is smaller than 1, then that means at the end this will be, or the outcome, or this term will be greater than the impact in the short run. And that means, because it takes time to adjust to the changed income, that means if you look at the total impact compared to only beta, so that means the ultimate impact of a change in income will be greater than the short run impact, which is the beta 0 in this equation. Okay, so we still didn't answer the main question. How are we gonna estimate this? So remember, so what we did, we started with the assumption that, or the observation that economic theory always, or in general, or in many cases, is expressed in a static form. So we're looking at the point of equilibrium, but this is a process rather than just a point. Okay, so ignoring, or if you don't account for this process, process that take us to equilibrium, then you ignore the dynamic aspect or the time element in the model, and that could be one of the specification errors too. So you need to think of that. And we looked at one of the very popular examples, which is the permanent income hypothesis, and how consumption expenditure in time t depend on not just income in time t, disposable income in time t, but also disposable income in previous time period. Okay, so then we thought how we would decide how many lags, the problems of multicollinearity, if we introduce more lags, etc. So how we're gonna deal with this? The correct transformation, what it does, it transform this a model, distributed lag model with infinite number of parameters to need to be estimated, into another form of autoregressive model, which has only 3 parameters to estimate. So again, we came to that point that we need to think of estimation, because before that, that was the problem with the distributed lag model. We were thinking of how we will estimate this model. Again, this model has some challenges too when it comes to estimation. So even if the original error term from this equation u t satisfy the conditions of all this estimation, then there is nothing to guarantee that the new error term, the composite error term, do you know what this VT now? So this is the new one. When we did the transformation, just let me go back to this. So this is the new error term. So this composite error term, so even if this one is or satisfy all conditions, then that doesn't necessarily mean that this one will do. Okay, so that's one point. Again, this is one of the challenges that we'll face, but this is not because, and given that it is likely to be serially correlated. So this is not a big problem because we studied autocorrelation and we know there are ways to deal with autocorrelation. But the major problem here, or the main problem here, is with YT. So one of the classical linear regression model assumptions we discussed in the first lecture is that the regressors, meaning the variables on the right-hand side, shouldn't be stochastic. And given that YT, the dependent variable, is stochastic, then that means YT minus 1, which is now among the regressors, is stochastic too. So that is a major, that's a key problem. Okay, so this is another problem. I mean, this one is not really a key problem, or the first one related to serial correlation, but this is the main problem. So if you want to estimate autoregressive model in this form, then you could actually so as I said, this is the heteroscedasticity, autocorrelation, consistent standard errors. This is something we discussed before to deal with the first problem. And the more serious problem is with YT minus 1, because it is likely that it will be correlated with the error term. And the solution to that, the way to deal with that, is to find a proxy. So another variable that is highly correlated with YT minus 1. YT minus 1 here is the consumption expenditure in time t minus 1, but yet is not, or is uncorrelated with the new error term. So if you find such a proxy, if you find such variable, then you could use it instead of YT minus 1 on the right-hand side, and then this is how you may be able to deal with this problem. So this is a very quick example of the first model. So let's assume that we have only the personal consumption expenditure depends on, this is constant, and this is the disposable personal income, and this is YT minus 1. So we just to simplify this, so we're looking at, if you go back to this example, so this is what we're estimating here. So this is the consumption expenditure in time t. This is disposable income in time t. And then also on the right-hand side, we have consumption expenditure in time t minus 1. And this is what we estimated using OLS. And now we understand this is a very, very problematic estimation, because we said with OLS, it is likely that this one isn't, this one is stochastic, and that is the most, like, the serious problem with this estimation. But if we ignore it for a second, if we ignore this fact for a second, because I said we can deal with other problems, autocorrelation, we can deal with autocorrelation, but again, the serious problem here of having a stochastic variable on the right-hand side, that means, and we say we need to deal with that using a proxy. But let's now assume that we know all of this, but we want just to look at these. How would we interpret these coefficients? So we know there are problems in this estimation. So we're not gonna really take it seriously or take it as it is. But just what I want to comment on is these coefficients. How should I look at these coefficients? For example, let's look at this one. What is this coefficient? 0.43 in this equation. This is beta 0. So what is beta 0 in this autoregressive model? We explained that before. So this is the short-run impact. Okay? So what is the long-run impact? How can we obtain it? So it's beta 0. So that coefficient divided by 1 minus lambda. So what is lambda here? Is the coefficient of the lagged dependent variable. Okay? So let's go back to this estimation and look at these. So what is this coefficient now? So this is beta. This is the estimated beta 0. Okay? Using all this. So I know it is very problematic, and we explain why. Okay? But just for a second, I just want to look at these coefficients and see what they mean. So then this is the short-run impact of the unit change in disposable income on personal consumption expenditure. So my question now is, what about the long-run impact? How would we calculate this? Again, do you remember? So it's beta 0. Yeah? Yes. So beta 0 divided by that, 1 minus lambda. So this is lambda. This is the estimated lambda hat. Okay? So this is lambda hat. So it is, then that means it's beta, this one, beta 0. So the beta hat 0, this one, divided by 1 minus this one. This should give you the long run impact. So again, we know there are serious problems with this, and the main problem here comes from the fact that we have a stochastic term in the right-hand side among the regressors. Okay, how would we deal with that? We want to think of this is the same estimation, but we deal with the problem of autocorrelation using the heteroscedasticity autocorrelation consistent standard errors, and this is very straightforward using AVU. So this is not a problem. So before we go to the other problem to see what we would do in the other problem, let's compare between these two estimations. So these should have the same coefficients. So if you look at these two coefficients, they are the same. So what is different is the standard errors. So the standard errors, these are corrected standard errors for serial correlation. Okay, and that's the only difference between these two estimations. So the coefficients are the same. So if you go back to this and you compare this column here, so it's exactly the same. So the difference only comes from the standard errors, because with the second one, this estimation, the standard errors are corrected for the presence of autocorrelation. And as I said, this is very straightforward, and probably we saw in how to do that in EViews. But this is not the serious problem. The serious problem is with having this variable yt minus 1 stochastic variable and on the right hand side, and we said we need to use a variable, a proxy, another variable that is highly correlated with yt minus 1 but is uncorrelated with the error term. So if we assume that, let's say, income in time t minus 1 is correlated with consumption in t minus 1, but is not correlated with the error term. This is not the best one to use. You could use wealth if you have data on wealth. So again, you could try to find another variable that is highly correlated. So this is the criteria. That's what we want to find, is another variable that is highly correlated with yt minus 1, the consumption expenditure in t minus 1, in time t minus 1. But is not correlated, is uncorrelated with the error term. Okay, again, this is just an example. As I said, this doesn't mean this is the best one that you could use. Again, you could find your own. It depends on the data on hand, so what you really have. Okay, so this is the idea with the autoregressive model. So again, let's start with the idea of having a dynamic model. It is very important we explain, because what we see in theory is often static, is often talking about equilibrium, but there's a process to reach that equilibrium. There's some adjustment to go to this point. Okay, and the example we discussed is the permanent income hypothesis of Milton Friedman, and we explain what that means. And then this give us the distributed lag model. And then to estimate that, there was problems, and then to deal with this problem, according to Coik transformation, we can transform this model into from distributed lag model to autoregressive model. Okay, then we avoid the problem of having infinite number of parameters to estimate, to have only 3 parameters to estimate. We still have a serious problem of having a stochastic regressor or a stochastic variable on the right hand side, and then we said we could go around this. We can deal with this by having a proxy or a variable that is correlated with yt minus 1 but is uncorrelated with the error term. So what now if we have both together? So the AR model, the autoregressive model, and the distributed lag model. So this will take us to another sort of dynamic model, where rather than having only yt minus 1 on the right hand side, you have t minus 1, t minus 2, up to t minus p. So this is the number of lags. We go back in time with consumption expenditure or yt in previous time periods. Also, so this is what we discussed. So this is autoregressive part. So this is the autoregressive part, plus the distributed lag part, which is the xt minus 1, xt minus 2, up to xt minus q. So again, this is the number of lags. We go back in time regarding the consumption expenditure. So this is the ARDL model, meaning that this is the autoregressive part. So this is the AR part, and then this is the distributed lag part. And P and Q, these are the number of lags. So P is the number of autoregressive terms, or the lags of the dependent variable, YT, and Q here is the distributed lag term, or the how many lags you would go back in time concerning the disposable income. Okay, so why would we do that? Why would we combine these both together? So first of all, we start with the distributed lag model. We say there are problems estimating this, and then we learn how to transform this into AR model, but now we looking at a model where we have both together, the autoregressive part and the distributed lag part. So basically this model has some advantages. It captures the dynamic effects of the lagged Y's and also those of the lagged X's. So it's not only the impact on YT, on the consumption expenditure that coming from the fact that income this year, this time period, and income in previous time period also affect consumption expenditure. Consumption expenditure also will depend on its own value in values in the past. So it captures this sort of dynamic effect. Also, you can eliminate autocorrelation, as I explained earlier, by introducing lags. This, if you have enough number, sufficient number of lags, this, of course, of both variables of X and Y, this will eliminate the autocorrelation problem. And in the seminar, I will show you how eViews can give you the best ARDL model if you decide the maximum lag, the maximum number of lags for P and Q. eViews will show you how to choose the best one among like many models. Okay, so as we said, there are some advantages. So let's think of estimating a very simple ARDL model. So so this might not be the best one to represent this relationship according to the data, but what we're trying to look at here is a very simple form of this model, just to see how we would interpret these coefficients. So this is ARDL1, meaning we have P equal 1, Q equal 1. So one lag for the dependent variable and one lag for the one lag of Y. Now it became part of the regressors or the independent variables, and also one lag of X. So consumption expenditure would depend on its own value in previous time plus the current income, current disposable income, plus the disposable income from the T minus 1, plus an error term. So just to simplify things, just think of this. This is consumption expenditure. The X here is the disposable income. And as I said, this is the ARDL 1. So that means we use one lag for the dependent variable, one lag for the X as well. And now what we need to look at is how would we interpret these. So beta 0, we know what beta 0 is. So beta 0 is the impact multiplier, or the immediate effect, what we called before the short run one. So beta 0 is the immediate effect when personal income, disposable personal income, it changed by 1 unit. The consumption expenditure would change by beta 0. So how about the long run multiplier? So the long run multiplier is the sum of these two, beta 0 plus beta 1, divided by 1 minus A1. Just remember, A1 here is the coefficient of the dependent variable in lagged dependent variable on the right hand side. Okay, so the long run impact will be beta 0 plus beta 1 divided by 1 minus A1. Okay, so there are some assumptions that we need to satisfy if we're going to estimate this model. One is the X and Y are stationary, and this is what we're going to discuss in the next half of the lecture, this lecture. The expected mean value of the error term ut is 0, and the error term shouldn't be serially correlated, and the x variables here are exogenous. Okay, so let's look at the estimation now. So what we have here, so we have on the left-hand side, YT is the personal consumption expenditure. On the right-hand side, we have disposable income in time t, and disposable income in time t minus 1. And also we have yt minus 1, the personal consumption expenditure in time t minus 1. So again, so what is the short run or the immediate impact now of 1 unit change? If a unit change in disposable income is beta 0. So what is beta 0 here? So this is the estimation for beta 0. Okay? So how much is the long run impact? So it's beta 0 plus beta 1. So where is beta 1? The estimation of beta 1. Of course, this is not beta 1. Okay? So is the coefficient of the xt minus 1. Let me go back to this. You see? So that's beta 1. So this one plus this one divided by 1 minus A1. A1 here is the coefficient of the lag dependent variable, which is here, 0.805356. So this is the estimation of A1. So should be this plus this divided by 1 minus this. That should give you the long run impact of a unit change in income. And again, this is the same estimation. This is the same model. The only difference is that we use the heteroscedasticity autocorrelation consistent standard errors. Any question? I should have asked it earlier, but as I told you before, like, you can stop me anytime. Okay, if you have questions, that's fine. Just please feel free to stop me at any point. Okay, so you don't have to wait until I ask you, do you have questions or not? Okay, so this is the first thing we wanted to discuss today. So before we move to discuss the next point or the next topic we want to cover today, let me just sum up what we did. So we'll start from a very important point, that it is important to consider the dynamic effect in any model, because that might cause, if you don't, that might cause some specification error as well. Okay, that counts as specification error. Okay, so when we talk about theory usually talk about equilibrium, but there is a process to go to equilibrium, to reach this equilibrium. And that's why it is important we need to take the time element or the dynamic element or the dynamic aspect of any model into consideration. So we started with the distributed lag model when we discussed the idea or the permanent income hypothesis of Milton-Friedman. Okay, and then we looked at a more generalized form of this model, and we said it's very difficult to have an infinite number of parameters to estimate, and that's why we need the Koch transformation. So when we do that, we transform the DL model with infinite number of parameters to estimate, or lags, then into an autoregressive model where we have only 3 parameters to estimate. Again, we have some issues, and we discuss what these issues are. Then we move to the sort of model that would combine these together, the AR process, the autoregressive part, and the distributed part. This is the Abdel model. Okay, so now we move to the next point, the next topic we want to cover, which is still related to time series again. So if you look at the Abdel model, they are time series, because you look at the lagged values and you look over time. But now, very important assumptions we made is that the data are stationary. So we need to know what that means. So in regression analysis, in general, we make this assumption that data are stationary. Stationary, that means that its mean and variance are constant over time. So they don't change over time. Mean and the constant, and also the covariance depends only on the distance between any 2 points in time. Okay, not on time itself. Okay, so it doesn't depend on time itself, and If a time series satisfy these conditions, it's known as weakly or covariance stationary. So where the problem comes from is the most serious economic series or microeconomic series is not stationary, okay? And we assume they are stationary. So what would happen if we use a non-stationary data or series in regression? So we'll see in a minute. But before I do that, this is the data we'll use in this part of the lecture. And by the way, the data now is on Blackboard under the folder data sets. So this data is about the exchange rate between the US dollar and the euro. And this is daily data from January 4th, 2000 to May 8th, 2008. So if you plot the data, that's what you see. So you see that kind of over time, it's not a constant mean at all or variance. So and instead it has like a trend like going upward with over time. So what is the problem here? As we said, mainly we assume that the data we use are stationary, or the OLS assume this is stationary data. So, but this is not the case in real life. Most data would not be stationary. But if we regress non-stationary time series on one or more non-stationary time series on the right-hand side, this might lead to what is known as spurious regression. Spurious regression meaning meaningless regression. And if you think of that, so if I give you a very naive example, if you run a regression, and this is something we discussed in the first lecture. I said, if you throw any data into software, you will get some results. So you should be the one who control this process. You should be the one who understand what is happening. Okay. So if, for example, if you get data for two variables that they are not related at all. So let's say your height and the GDP. Okay, and if you regress these two together, you might get significant results. Okay, meaning your height determine the GDP. It doesn't make sense. Or your height determine your income, for example. It wouldn't make sense. Okay, so these are two unrelated variables, but because both variables move with time, they progress with time, yeah. So your height and probably GDP as well. Okay, that would make them seem to be related if you use a regression model, but they are in fact not related. You might have a very high R-square for this sort of relationships, spurious regression or meaningless regression, and statistically significant regression coefficient, but this is something you can't rely on. So you can't tell me that your income depends on your height or GDP depends on your height. That's the idea. As I said, both variables just move together over time. This doesn't make them related in any way. And that's what we mean by spurious regression. And that's exactly what happened when we have when we run regression of non-stationary time series. Okay. So how would we know whether we have a stationary or non-stationary time series? So there are different ways to do that. First of all, you need to graph your data. You need to plot a graph of your data and look at your data and how it looks like. And this is very important, by the way. So any data you have, you need, before you jump and do any econometrics, just look at your data, understand your data first. And this is something we raised in the first lecture as well. We said we need to do that. Or you can use the choreogram, or you can use one of the unit root tests, as I will show you now. This code just says exactly the same thing I just said now. You need to examine your data. You need to look at your data. So if you do that, if you analyze any time series data without plotting them, so that means you're asking for trouble. You need really to look at your data. Okay, so it's very important to look at your data. When you look at your data, it might give you like an indication whether the data, so basically, even before we do this, If you go back to this, there's a kind of like it looks like it's moving, like upward trend, moving with time. So it tells you it doesn't have constant mean or constant variance. So it's very easy to depict this in some cases if you just plot your data. Okay, obviously you should do some formal test as well, and that's what we're gonna cover now. But again, if you plot the data, or if you plot here the other one we plotted against time, but this one is the exchange rate in time t. Again, it's the exchange rate in time t minus 1, and you see how closely they are correlated. So that tells you this series is not stationary. Okay, it's away from being stationary, far away from being stationary. The other way is to look at the autocorrelation function. And the autocorrelation function would show you if the correlation of time series over several lags decay quickly or slowly. So if it decays slowly, so if it disappears slowly, it is very slow, that means it is non-stationary time series. Here's how this is defined, or how this is calculated. The autocorrelation function at lag k would be the covariance at lag k divided by the variance. Okay, of course you can use any criteria to decide how many lags to use, and also you could, as a rule of thumb, you could follow this. You could compute the autocorrelated function up to 1/4 or 1/3 of series length. Depends how many data points you have. Okay, so there's like two different ways to up to what lag, how many lags to go back in time. But this is not the problem here. This is not what we're looking at. We want to look at the plot of because this row, the autocorrelation function, we usually use a sample to get this. So this is the row hat. So it just comes from a sample. And if you plot this, the plot of this, it will give you what we call the correlogram. So correlogram is just the plot, is a plot of the autocorrelation function, and it's something that you can find out. You can compute its standard error, or you can test whether it is statistically significant or not following this Q statistic. This is how you calculate it. Okay, and again, this is something that you don't need really to worry about much, because it's very easy to produce these days using software like eViews. So if we look at this, for example, so this is the correlogram for the series that I just showed you, the exchange rate. And if we just ignore the partial autocorrelation function now, so let's look at the autocorrelation function. So the idea here is that how fast or slow it decays over time. So what I'm showing you now, it's up to 18 lags, and it is very, very slow decay. So it's not really going, or it doesn't decay very quickly. It's very, very, very slow. So again, this would give you an indication this is a non-stationary time series. So again, this is just another way when you just analyze or look at your data. So you could graph your data, you could look at the correlogram, and again, as I said, this is an indication. If you look at these numbers here, it just doesn't go down very quickly. It's very slow. And again, if you look at this is just a representation of this. So again, it is very, very slow. And this tells you that this data isn't stationary. This data is non-stationary. So another way to do this, or a more formal way to do this, is to follow a test, a unit root test. So the unit root test for our series, the exchange rate, will be expressed as this equation. So you have the first difference of the log of exchange rate. You regress this on a time trend t, and on the exchange rate in time t minus 1. Okay, and so the null hypothesis is that this beta 3 equal to 0, or that this series has unit root, this one. Okay, The alternative is that beta 3 is less than 0. So if you fail to reject the null hypothesis, that means the series is non-stationary. Okay, and because we can't use the t-test, Dick and Fuller, they provide this tau test, and they provide the critical values calculated by simulation. So rather than using the t-test or t-distribution, you can't do that. So you follow the t or the tau critical values. And if we estimate the this equation by OLS, this one, this is what I'm going to show you now. Yeah, so this is just the estimation of what we've seen now. But we can't look at this t statistic and compare it with the t critical value. We need to compare it with the tau critical value that's provided by Dick and Fuller. Okay. There are three cases, just before we move on, of Dickey-Fuller test. So in this one, we introduce only one case, but there are three cases where or different forms. So the first one here is known as random walk. So you don't have constant, you don't have time trend. So no constant or time trend. The second case, when you have random walk with drift, so because you have a constant. And the third one, random walk with drift around deterministic trend, where you have both. You have constant beta 1 and when you have t as well, the time trend, and they have the same null hypothesis. And again, you need to look at the critical value that are provided by Dickey and Fuller. So the other form of this, because why would we go back only one lag? So why we go only back to t minus 1? We could go back further, and this is what augmented Dickey-Fuller test provide us. So what we have here, we have exactly the same equation. So this is the constant, the time trend, the lagged value of the dependent variable in time t minus 1. And also we have the sum of the delta, the difference from 1 to m of the dependent variable in t minus 1. Okay, so now the m here is the maximum lag, is the maximum length of the lag dependent variable. So how many lags you gonna use? Again, you can use one of the criteria, the information criteria, to decide up to what lag, how many lag you would use. Okay, just to move on then, so let's see an example. So here we have the first one. So this is the unit root test, the Dickey-Fuller, augmented Dickey-Fuller test in views, and this is how the output look like. So what we need to look at here? What do we need to look at? So what is the null hypothesis? So you remember? So going back to this, yeah. So the null hypothesis that beta 3 in that equation, which is the coefficient of the lagged variable of the dependent variable lagged in time t minus 1, equal to 0, and the alternative is beta 3 is less than 0. Meaning that if we fail to reject this null hypothesis, that means the series under consideration is not stationary. Okay, so if you reject, that means it is stationary. Okay, so let's go back to what we did. So again, so which case we have here in this actually it doesn't show the, yeah, actually I said it's an intercept. So this is the first, not the first case, sorry. This is the random walk case with drift, because we have intercept. Okay, so I just put in the title of the slide, but it I shouldn't ask then. It is there. Okay, so and actually you wouldn't know unless I show you the second part of the output, the eViews output. Okay, so this is the second part before we look at this part now. So this is what we have. So what we have on the left hand side, we have the first difference of the exchange rate, log of the exchange rate, len EX. And on the right hand side, we have len X in time t minus 1, plus we have constant here. That's why this is the this case, going back to this. Yeah, so this is this case where we have random walk with drift. Okay, so the question now, yeah, so now let's how to make a decision. As we said, then you see the null hypothesis is that this series has a unit root, meaning that it's not stationary. Okay, so the exogenous here is constant. That means we had an intercept. So the question here is that because we can't use this, and look at the t table or t critical values, then we need to, if you actually provide the values that you need to look at. So we have the t statistic here, and these are the critical values. That is the ADF critical values. But again, you could just look at the probability value associated with this just to make a decision. So given that we have the big B value, that means we fail to reject, or we reject the null hypothesis. Do we reject or we don't reject? Or yeah, so we can't, so we fail to reject. So meaning that we don't reject the null hypothesis. So if we accept or we don't reject the null hypothesis, that means the series has unit root, means it is stationary or non-stationary. It is non-stationary. It is not stationary. Okay, and we want it stationary. Just remember. So non-stationary series is a problem because regression that include non-stationary series could lead to spurious regression. Okay, so we want to avoid this. That's why we examine the properties of the series on hand. So in our case now, we're looking at the exchange rate, and what we found is that this is the it is a non-stationary series. So this is the first, if we have it with drift, this one with both. So we have trend and intercept. So again, the same decision. So it is non-stationary. So we can't reject the null hypothesis, and since we can't reject the null hypothesis of unit root, that means it is non-stationary. It is not a stationary series. Okay. So if we omit both, so if we have only just random walk, so we don't have a constant or time trend, again it gives us the same conclusion. So this is not a stationary time series, and we can't. I mean, we need to use it. We need to understand that. We need to because in some models that we covered, we can't really use non-stationary time series. So the question now is, what would we do then if we want to convert or transform this a non-stationary time series into a stationary time series? So one way to deal with this, is it clear, the test and what it does? Okay, it's very straightforward really. It's just you need to know how to do this in eViews and how to make a conclusion or decision. And also it is important because if your assignment as well, if you're dealing with time series data and you don't plot your data, then there's a problem here, yeah, because you really need to show that you understand that you need to plot your data. Have you started work in your assignment? Choosing the topic at least, collecting data. Okay, so yes, yeah, I think I know we discussed this last week. I understand. I think now it is not that the reason is not working data stream on computers now is because of the new subscription. So we have a new license now that we need to use for data stream to work. And what I understand is that there will be a link for students that will be distributed with like some information on how to access it and where to access it. So did you try the UK Data Archive? Do you remember last week I told you if you just put in Google UK Data Archive and then you use your student number, then probably you will see how to sign up for. No, that's fine. You try that one. So let's just go back to this. But if you, my question was, if you haven't started really working in your assignment, then you need to start doing so as soon as possible. Because you need to start from the beginning. You need to find a research question, and then you need to find which what data you're gonna collect, and then which econometric technique you will use, and then how you're gonna write your final report. This is really important. So let's go back to the idea here. So before we go to the point where we discuss how to make an unstationary or how to convert an unstationary series to a stationary series, let's just sum up quickly this idea. So the idea is that what is a stationary time series? Means its mean and variance are constant over time, and the covariance between 2 points just depend on the distance between 2 points in time, not on time itself. Okay, so that's one thing. And we said that in regression models, in regression in general, we assume that series are stationary, and there's a problem of running regression of non-stationary series that you could fall in the what we call the spurious regression. So you could have a meaningless regression, and the very naive example I gave is that if you run regression between your height and GDP or your income, you might find significant results and might give you significant coefficient, which is obviously is not true. Okay, so your height wouldn't determine the GDP or your income, or your height wouldn't determine the your income as well. So how to detect that? How to examine the data in hand? Then you could plot your data, and this is something that you are encouraged to do in all cases, whether you're looking you're detecting for stationarity or not. In any case, you need really to plot your data. Also, you could look at the choreogram where you look at the autocorrelation function and how fast it decay over time, or using over lags, using different lags. And you could do the unit root test. And by the way, there's just different tests of unit root, not just the AD-Fuller test or the augmented Dickey-Fuller test. So now at least we know one of these tests. So now the question is that when we find data series like this, time series data like this, the exchange rate, non-stationary, what should we do if we want or if we need to make it stationary? So the first case, when we have trend stationary, so if the data is stationary around trend, so you could just detrend the data or remove the trend. How would we do that? So if you run a regression of the series on constant and time trend, so you have time t here, so the residuals in that case, this will give you the detrended time series. So v hat here is the detrended exchange rate time series. Okay, so that's one way to do this. So if we do this with the series in hand now, so somehow you could think of this. Sometimes it's not really easy to look at the graph, but this is the original time series that we saw before. And when you detrend it, this is how it looks like when you detrend it. So how did we do that? This is the residual from this model. Okay, so this is the residuals after regressing the time series on time trend. So take the residual, and this is the detrended series. And again, this is the original one, and this is how it looked like when you detrend it. So somehow now, like if you look at it properly, it doesn't have the same trend over time. It's not going like with an upward trend. So you're still somehow looking at some variation around. It's not constant. It's not really easy to decide whether it's constant mean or not. But still, if you, for example, if you have line from here, so you still can think of this as something going around because there's no trend anymore. So it could be stationary. So if you want to make sure about this, then you could just do the unit root test, like here. So this is the top section here is the original series. So this is the test we did before. So it is non-stationary. But then after detrending the data, so this is the detrended exchange rate. So what's happened here? You reject the null hypothesis. Okay, so again, when you reject the null hypothesis, meaning it is stationary. Okay, so if you fail to reject, so it's not stationary, it has unit root. But now, so this is what happened when you detrend the data. Okay, so we detrended and again, how to detrend? So it's a very simple way to do it. You could run a regression of your series against or on time trend, and then you obtain the residual. That will give you the detrended series. Okay, and this is an example. So in this case, this is the test for the original data without detrending the data. So this is the original series, and you fail to reject the null hypothesis, where here you reject the null hypothesis of non-stationary time series data, which means it is stationary time series data. So another way, so the first one, if this trend stationary, then you could just detrend the data, and that would solve the problem. Another way you could, this is something. So another way you could do this, which is the difference stationary, which means if you take the first difference or you difference the data, this might solve the problem. It might be, and in that case, it's called difference stationary. So how does that work? This is how it looks like when we take the first difference. So if you compare this graph, so this is the original time series. So it has like upward trend, and it is very obvious it's not stationary. When you compare this to this one, so it's going up and down, okay, around constant mean over time. So that is the first difference. Okay, so it's very obvious now that this is stationary. Now it became stationary. Okay, so even if you look at the choreogram, so remember, it is decaying very fast. Like now it's 70. Like if you compare this to the one we had in the beginning for the original series, let me just go back to to this one. So you see how slow this decay, how this slope becoming smaller. Okay, and again, it doesn't, even if you go, I think if you go even through 50 lags, is not going to decay any faster, because it is non-stationary. If you compare this to this one, where is it? So you'll see it's getting smaller, it decays very, very quickly. Again, we do the test. So in this case, so this is the unit root test for the first difference of the exchange rate series. And what we have here, we reject the null hypothesis, meaning now it becomes stationary. So it was non-stationary series, it wasn't stationary. And then when we detrend the data, the first one, the first case, it became stationary. Also, when we took the first difference, it became stationary, and we confirmed stationarity in both cases using the unit root test, and also we graphed the series. Final remarks before I conclude. Okay, if a series becomes stationary after differencing it once, that means it is integrated of order 1, because you difference it only once to become stationary. So it wasn't stationary, it was non-stationary series. Then you take the first difference, then it became stationary. That means it's integrated of order 1. So if it has to be differenced twice to become stationary, so it is non-stationary, you take the first difference and then you difference again, or you take the second difference. That means, or you difference twice, that's what I mean. So that means it is I2, so integrated of order 2. If it difference t times to make it stationary, that's why if you needed to do it d times, 3 times, 4 times, well, however, how many times you need it to, To become a stationary, that means it's integrated of order ID. So it depends how many times you had to differentiate until it become stationary. And a stationary time series in the first place is integrated of order 0, so it's I0. So when we say I0 series, that means it is a stationary series. So the series we had, the example we had, the exchange rate series, is it integrated of order 1, 2, 0, 3, how many? The exchange rate, this one. So how many times we differentiate to become stationary? Only once. So it's I1. So that's the idea. Okay? So the idea is how many times you had to difference the data to become stationary. In this case, it was I1 because it is I1 because it wasn't stationary in level. So the data we had for the series wasn't stationary, and we confirmed this using the choreogram, or we looked at the unit root test, or we looked at the graph. So we know it is not stationary. But when we differentiate once, it became stationary. So we needed only to difference only how many times? Only once. So that means that make it I1. Okay, so that means the exchange rate, the series we had, is I1 because we had to differentiate once to become stationary. That means it is integrated of order 9. But if it was a stationary in the first place, so in level, that would have mean that could be it would be called I2 or integrated of order 0. Okay, so just like as I said, these are just final remarks before I conclude the lecture and ask you if you have any questions again, if you have any. So an I0 series fluctuates around its mean. We know it's a stationary, so it's going up and down around constant mean and constant. It has constant variance, so it's the same mean and constant variance. If you compare this to an I1 series, which meanders widely, so it goes up. Like the first series, you see, like it has an upward trend, so it doesn't go up and down around a constant mean. So an I0 series is mean reverting, meaning it goes back up and it goes back again to the mean, whereas an I1 series doesn't show such tendency. An I1 series can drift away from the mean permanently. So if you go back to the first graph we had for the exchange rate series, you see it drifts away from the mean, and that can happen permanently. And that's why it is said it has like a stochastic trend, so it's going upward. The autocorrelations, we discussed this before. The autocorrelations in choreogram of an I1 series decline to 0 very rapidly as the lag increases, while those of I1 decline very slowly, and we show this in the first example. Okay, most non-stationary economic time series, and this is very important to know, don't need to be differentiated more than once or twice. So in most time series you will deal with, probably it's could be I1 or I2. So it's very unlikely to have a series that's I3, for example, or you need to differentiate 3 times to become stationary. So most time series you will deal with in economics, probably it will be either I1 or I2, meaning that they are non-stationary in level, and you need to differentiate either once or twice to become or to make it stationary. Any questions? Is it clear what we said? So can you just very quickly look at what we discussed the first topic? What we looked at, dynamic models. Why do we need to consider dynamic models? Do you remember? You don't remember, you came late. I know. Okay, so remember, when we talk about equilibrium as a static point, the way it is expressed in economic theory might lead to specification bias Why? Because there is a dynamic element, there is a time element, there is a time factor that we need to consider. Okay, and that's why we need to consider of dynamic models, where we look at not just t minus 1. And a very popular example we discussed is the income, the permanent income hypothesis of Milton Friedman, when where consumption expenditure depends not only in income, disposable income in time t. So the consumption expenditure in time t doesn't depend only on income, disposable income in time t, but also disposable income in time t minus 1, t minus 2, and up to, as they estimated, like up to 16 lags. So, and then we look at the a more general form of this model, where we have distributed lag models, where we have infinite number of lags of the independent variable of x's. Okay, what was the problem with this? How can we estimate this? You wouldn't be able to estimate infinite number of parameters. Okay, so we use the Huygens transformation to convert this to transform this to a AR process. So autoregressive model. Okay, where yt depends on yt minus 1 and xt. So that make it from infinite number of parameters need to estimation, then to only 3 parameters need to estimate. And then we discuss the issues with these sort of models. And then we discuss the case where we have both together, the AR model, the AR process, and the distributed lag process. So we have both. So an AR deal model, and we explained how to interpret the parameters in this case, the estimated parameters. And then one of the assumptions we made about this is that the data are stationary. Then we move to explain what stationary means. Okay, so stationary, we start mean and variance are not changing over time, so they are constant over time, they are time invariant. And then we'll also talk about the covariance between any 2 points depends on the distance between time, not in time itself. We explain how to detect this. So you need to plot your data, you need to look at a choreogram, you need to do a unit root test. So what if you have a non-stationary data, and you most likely to have a non-stationary data if you deal with time series data, then that means, or if you deal with economic or finance data, so you're more likely to not find, it is really, in most cases, you will find non-stationary data, not stationary data. Then you need to, if you want, or if you have to make it stationary, then you could, if there's trend stationary, means that you could just detrend the data, that will make it stationary, or difference stationary means that you difference data, and this will make it stationary again. Okay, and we concluded with some remarks or some points related to what the integration, the order of integration. So if we have a stationary series, that means it's I1, so it's integrated of order 1. And if we have a non-stationary series that you need to difference once to make it stationary, that means it's I1. If you need to difference it twice, that means it's I2. And we said most economic series you will see are either I1 or I2. Okay, so it's very difficult, or it's not really expected that you're going to have any order more than higher than 2. So it's unlikely you're going to have I3, for example. So I've never seen this. Okay, so most series will be either I1 or I2. Okay, any questions?